So, my name is Toke Eskildsen, or Toke Eskildsen, I think it is in English. I've been working for, 8 years at the State University Library in Denmark, and for most of these years I've been working with our search system. And in the later years, actually about 1 year ago, we decided to try and index our harvested web resources. This net archive, as we call it, has been running since 2005, yes. And the current scale is about half a petabyte and, 15 billion entities, something like that. So, we would like to have free text in that because we like our free text. And it was a fun challenge. So, first thing, Andy made his presentation, and he described the setup, which is done in the way that you would normally make a Solr setup, which is to build a cloud and let Solr handle how documents are routed between shards in order to index all this stuff. So this has some advantages. Among one thing, that your shards will be about equal size and the content will be mixed between them. It works well for updates and searches. You might have some bottlenecks indexing. I know that. Sorry?
May I ask a very stupid question? A shard, is it a part of an index?
Yeah, a bit of a step back. Thank you. So, a Solr index is made of one or more shards, and each shard can be seen as a separate index. That's at least one view. You can search in a chart independently of the other shards. In a SolrCloud, you virtually treat the collection of shards as one big index. And what SolrCloud takes care of when indexing is that the right documents, in case of an update, goes to the shard that contains the previous version. That's sorry?
There's no merging shards.
You can merge shards and you can split shards, and you will do at some point probably if you're running a setup like this. So, yes, that was the splitting and moving part. There's some problems with running a very large SolrCloud. One of them is if you want to rebuild your index because you have some fundamental change in schemas. In some cases, you really need to do it parallel to the existing one. So if you have this very huge cloud with 10 terabytes of index, well, then you need a comparable setup to build a parallel index before you switch over. So there's this whole generation problem in having these large instances. There's also another problem, that is that it takes more resources to do it that way. Because, let me see if this is the next slide. Nah, I think I have messed up the order of these. Let me skip why it takes more resources to do it that way, and instead try and describe how we can optimize this whole sharding process. Because instead of treating the whole index, both index-wise and search-wise, the whole collection of shards, both index-wise and search-wise as a complete index, we can actually build the shards independently. And then we can store them, and we can search across the shards. So there's a huge difference here, because suddenly we're changing from a live index, as Andy describes, with its pros and cons, to a static index. Each shard is built once, put on a server, and it's never touched after that, theoretically. In practice, we will rebuild them at some point, but we won't update documents within that shard. So, how does such a setup look like? Multimodal presentation. Well, it's quite simple. This is our index on an abstract level. Then it has a shard 1, it has another shard 2, and so on. And we can have an endless amount of these, theoretically. I know some people has been running with 1,000 shards, which seems to be about the limit of what Solr can take. more realistic numbers don't go beyond 50 or 100 shards, depending on who you're talking to. There are some problems with a very large scale. Anyway, if we see these from a building point as separate indexes, well, we have some magic box over here that produces a shard 3 in this case. And when it's finished producing that shard, it says, okay, nothing changes anymore. We just put it over here in our collection 3. And we're good to go. So, what does that give us? Well, the point is, when we have these immutable shards, we can actually optimize them. A live solar index is a collection of a lot of smaller segments, they're called. I think, Andy, your setup has 130 individual parts in a shard, and those can be optimized down to 1. That saves a lot of resources at search time, which means we don't need as much memory for it, and we get better performance because it doesn't have to do all this mapping between the inner parts. So what you see to the right here is actually a screenshot from one of our shard servers, which is running these, as you can see, 250 million documents. It's 900 gigabyte large, and it uses about 4.5 gigabyte of heap in the JVM, which for those of you who have played with Solar is very little compared to a normal setup with a shard of that size. But that's because it's read-only. So for this machine, which does nothing but search, well, lower the RAM requirement, the higher the performance at a basic level. The only downside, that's a lie, but the very important downside is that we cannot update individual documents inside of these shards. If you want to update a shard, we need to build a new shard and replace the old one, which is, by the way, easier than rebuilding the whole collection of shards and replacing them all at once. So we can do a rolling upgrade of the shards. So that takes care of the generational issue when we learn new things and change those schemas. So how do we build these shards? How does it work? Well, we want shard of a certain size, whatever we decide on. We decided on 900 gigabytes. We like that size. I'll come to it later why we like that size. So, in order to do so, we piggybacked on the work from British Library. They made this very nice, I think it's called WAR file discovery.
Web Archive Discovery.
Web Archive, yeah, oh, I wrote that. Web Archive Discovery. So, that really means that we have this, what should we call it, VAD, something like that, which takes a bunch of ARC files from here, processes it, and puts it into a builder, which builds shards 4. So our only architecture, our only addition to this is that we build a little system up here, which we call Archer, which looks at this Solar installation and says, how far have we got? How large is the index right now? If it's beyond a certain level, we'll just keep spawning those indexes.
What is that?
That the archive discovery?
Archon.
Archon. That is just a controller. It's tracking the WARC files we have indexed and issues new workers to build a new index.
Is it something you developed? Or?
It's something we developed. It's on GitHub or this location. But at its heart, it's really very simple. It's not rocket science. It is really just keeping track of which ARC files we have processed and if the shard is large enough.
Okay.
So, if shard not large enough, keep indexing ARC files. When it's large enough, optimize it, finished. So, the logic behind this is very, very simple. And it works very well. It turns out it's actually easy to hit this intended size of the Solar shards. We have 25 shards running, and they're between 885 and 905 gigabytes. So the margin is quite low. We could spend some more time and hit 900 more precisely, but we saw no use in optimizing that case. So for this indexer, we're not using Hadoop. We could use that, that's absolutely not a problem. We just have a single machine, runs a single Solr, runs a single tracker, runs a single spawner of these Web Archive discovery things, which actually do all the heavy lifting. This Web Archive discovery TCAT process uses all the CPU on the machine. Solr can keep up with that, no problem, at least when you only have 40 workers running. So we've been quite happy with that. It takes, for us, 8 days to build such a shard. So it took us half a year to get where we are now.
8 days?
For a single shard, yes.
Well.
But I'll just finish this. But the point is, as all the shards are independent of each other, if you have 2 machines, you can produce 2 shards in 8 days. If you have a Hadoop cluster of enough machines, you could do your whole archive in a week, because it's independent.
Okay.
Sorry?
Could you just clarify the first line saying it's not a standard Solr? In what way is it not standard?
It's not a standard Solr setup. I should have added that. It's just because we're going away from the standard SolrCloud, which says a cloud is something that is responsible for indexing as well as searching, and they say we only use it for search. But thank you for asking. Okay. Of course, it's on GitHub. You could use this for controlling your articles, but you could also just create small batch jobs which indexed ARC files using this WARC file indexer and then writing in a log file which we had processed. This is really just to make things work easier for us. Yes?
The 250 million docs, what kind of docs are we talking about?
That is web resources.
Web resources.
The images, web HTML pages, PDFs, whatever you have in your web archive.
Around 250
Yeah,
million.
I think it differs between about 200, I think we have 330 million in one chart.
All right.
We don't really care. We care more about the size of the index.
Yeah.
And as Andy taught, single Solr shards doesn't really like to have too many documents, and the exact numbers kind of depends. So we also like to keep in this lower end of the 100 of millions documents, because that's a fine spot for Solr.
Okay.
So let's have it all even out. It evens out. Okay. So does this work? That's a good question, because the indexing part works at least. We can prove it, and the parallel indexing means that we can scale if we really wanted to speed up our indexing processes. The only bottleneck is how fast we can deliver ARC files from our underlying storage. And that's I don't really know what system it is, but the guys claims that that's not the bottleneck, so we're just happy about that. So we want to measure. And I'm really not interested in indexing performance, sorry. We can talk about that, but I haven't measured that very well. But search is really where I like to play. So in order to have a fair idea of what the performance of such a system is, well, the only real rule is try to make your performance tester behave like a user, because that's what's relevant. And for you can see I listed, it means please don't repeat queries too much. They will be cached and they will be unrealistically fast. If you have logs, it's super. For a project like this, it's actually a big challenge, because we have no logged searches because the project doesn't exist yet. So we have to simulate what we think are user searches, which is inherently problematic. In reality, we just take random words from a Danish dictionary and hit it with that. Ensure that your system is warmed so that it will operate as it would in a realistic situation. Maybe you need to have more threads running at a time. Really depends on how many users you have. And do not trust this queue time that Solr says. Really measure from the outside. What is the real time? Because what we have discovered is that while the internals of Solr can be insanely fast at some time, well, when you need to serialize the end products and get the huge XML result, that can actually take a second or two well, at least we've seen that for some of our results. So nothing magic here. It's really what you would read if you go around and see how you do performance testing. And one thing that I talked with Andy of yesterday and the day before that, do remember to capture how the machine is, how much free cache memory it has, how large the index is. Just when you look at your numbers a few months later, you would be glad that you actually remembered what you measured. But again, plain sense. So now we have a method of, or at least an idea of how to measure stuff, but we don't start out with a finished system. We're trying to predict how our prototype, how our test setup, or whatever we start with, how will that scale? And the point is, when we scale things up, well, it usually goes like, well, now we have twice as much and it takes 3 times as long, and so forth. So really do remember to scale multiple points when you're scaling up. So if you have a machine and find out how much it can take, measure with 2 shards of 100 gigabytes, 2 shards of 200 gigabytes, 2 shards of 300 gigabytes, in order to get an impression of how if it's a logarithmic or a linear progression that we have here. Do test on 2 shards. Solr has vastly different performance metrics whether you're running a single shard system or a multi-shard system. And do visualize. I'll come to that in a bit later. So the part about 2 shards, why is that? It's because when Solr performs this distributed search, which it does always when you're searching in more than 1 shard, it's really a 2-phase system plus a final merge. So first phase, well, it's a search for your terms, and it's a faceting call if you're using faceting, which everybody in the world is. Phase 2 will deliver the documents that we determine to be the best ones from our result, and do some fine counting with faceting. I think that gets a bit too technical to explain why, but it's needed to get proper facet results with proper counts. And that's actually also a heavy process. And then there's the coordination and merge overhead, which thankfully is very low in itself for Solr. It's just, I don't know, a few milliseconds, 10, 20 if you have these 25 shards. So it's not really a factor. But this second phase means that just running 2 shards, each of half the size as running 1 shard, you could say, will be slower. We'll test with that. Okay, visualization time. So how do we investigate these measurements we've made? We have run a test. We have a lot of response times, and we want to make some sense of them. So one thing, I actually just made this yesterday. We haven't used it for anything, but it's a very popular one. Getting an expression, how many of our searches are very fast, and how many of them are out there being horribly slow. You don't take this for production data because, as I said, our searches are for random words in the dictionary, so they're not representative of a real use scenario. This is just an example of how you could visualize and get an idea of data. So, other thing, well, just plot the response times. This is a mess. This is a mess of testing 2 ways of searching, and I can see that the blues are somewhere, there seems to be a line, and the purple ones are all over the place. So I can't use this for anything.
Well, was it measured from real-life users?
Well, that's the problem. This is from a net archive, so it was measuring with random words from the dictionary.
Ah, okay.
So it also makes sense they're all over the place. But there's actually a system in this, and we can find it. So first, we switch and then say, oh, let's look at how many documents we found and how long it took to find these documents, the hit count and the millisecond. So hit count as X, millisecond as Y. And as we can see, that didn't help much because we have this huge thing to the left, but we all love our logarithmic scales. So again, what we see here is a picture is beginning to show that says, well, as long as we have fewer than 1,000 hits for the setups, response times are quite fast. They're below 400 milliseconds. When we move between 1,000 and 1 million hits, they seem to jump to double that, and there's a bit of a fall off maybe, and then they jump again when we get to this 10 or hundreds of millions of hits. We can visualize that even better. So, hopefully the picture is becoming clear here. This is a candlestick diagram. You could look it up. What it really shows is the percentiles and the median for the individual buckets of searches. So, for example, if you look at the purple one for 1,000, or was that 10,000, whatever, hits, we can see that the median, which is the black line in the middle of the candlestick here, is about 500 milliseconds. And the 95 percentile is below 1 second. So we kind of like this. I think this was for 12 terabyte, by the way, as far as I remember. Something like that. What we can also see is that this has quite a distinct shape with a little hill in the middle, getting a bit better, then getting worse as we enter these tens and hundreds of millions of hits. Okay.
Do you have a feeling for what happened at 10 to the 6, why that's so different?
Oh, I'm glad you asked that question. This was actually Andy that discovered it. He called it the pit of pain, very graphically, and it is a pit of pain because it's very, very ugly. Now, the purpose of presenting these visualization ways is, of course, because now we're moving into a case study, which is our setup, where I will use these presentation diagrams all the time. So I hope if there's something that is unclear here, so please ask. I know not everyone is familiar with percentiles and candlesticks, but can I clarify in any way? No? Everybody's familiar? Or nobody dares say anything?
What were the upper and lower parts of like the...
Yes, the lower part of this candlestick is the absolute minimum time.
Okay.
The upper part is not the actual maximum.
No.
It's a 95 percentile.
Why?
Because it could have maybe I should have made it 99 percentile. But anyway, the problem with running Java is basically at some point you're hitting some garbage collecting things.
Right.
So even for these very, very nice response times, if I put the absolute maximum, we would have something up here.
Right.
And it wouldn't be representative.
No.
But it's another study. It would be very nice at some point to investigate what are our maximum times. But that's not the focus. This is to get an overview of how is the performance for most of the users, for 95% of the searches.
And the boxes that are...
The upper limit of the box is 75%, the lower limit is 25%, and the what's it called, the black line in the middle is the median.
Okay.
So
the
there.
last candlestick is the lower and the 25%.
Problem is I only ran these tests with about 1,000 queries, of which only 600 and 500 returned a result.
Okay.
And it only ran for 10 minutes, so we're missing some points in the right end.
Okay.
I should probably make it with, I don't know, 10,000 queries and let it run for an hour instead. That would be better measurements.
All right.
So the data is a bit dirty out to the right because we don't have that many searches that hits that.
Okay. Thanks.
But thank you. Okay. At an abstract level, just to reiterate what Andy said, and because I made my slides independent of his, what we need to get Solr performance? Well, there are really two issues here. And one is the IIPC, the in-out operations per second, or in the case of these read-only shards, in operations per second. And they're mostly good for many users, many parallel users. Because Solr is very much a single-threaded process through each core. So we have these 900 gigabytes of data we issue on each core. We issue a search. Well, it will perform a lot of random reads sequentially in the data of that shard. So it really means that we want each data retrieval to be as fast as possible. We want the lowest latency possible in order to get a proper single user experience. So high IOPS, great for multi-user, low latency, great for single user experience or the single search. And of course, if your latency is lower, you will have more IOPS. So lower latency is a solution to everything. So the slowest media we have at Statsbiblioteket is tapes. I wouldn't recommend running a Lucene index on that. But it would be, I think it would actually be possible with the way we mount our drives. Then current technology, the spinning drives, they're dirt cheap. Next up in the hierarchy of speed is solid state drives. And of course, currently RAM is the fastest thing we have for storage. As Andy said, well, currently we have 22 terabytes indexed, and I don't know how much that would cost in RAM, so we're not going there. So we need to somehow find the best combination. What works is a spinning drives with a lot of RAM, is a solid states with less RAM, hopefully. So we mix, and this is where we need to go.
What kind of storage you are using? Probably that's the next slide.
Yes. So, to answer your question, this is our full indexing and search setup currently at Statsbiblioteket. So, it's 2 machines and a drive array. And it really is that. It's full now. We have filled the 25 shards, and we have indexed, I would say, about 40% of our harvested material. So we have ordered 2 new machines, which are a copy of the 2, what's it called, rack entries, racks, the 2 machines at the top, the search machines, in order to hold the rest of the index and to have some room for when we harvest more material. I would say the lower machine, which is responsible for the building part, it only indexes, is vastly overpowered with regard to RAM and storage. It really isn't necessary. Why we bought that that's a story for when we have the pint of beer.
Is it fiber channel?
I wouldn't know.
Nice,
It is local storage, so there's a controller on it, which is capable of handling 25 drives. So, so as close to the metal as possible. What happens underneath the hood, I can find the spec for you.
No. If it's a local storage, then it's not fiber channel, probably.
No. To anticipate a question, I can say that when I ran some tests, I looked at the number of IOPS on the whole over the 25 shards, and it peaked about 90,000 IOPS per second when we hammered it very hard. So that's about the level that we are requesting from the array. I don't know if that helps. Moving on. So what are we doing with this? Well, we are of course using free text search, which is a lot of stuff. But for us, we don't do much in the way of fanciness. It's really just, well, we have these about 6 fields that we're matching in, and we do this phrase matching, which means that you can quote a piece of text and find that in the corpus. And then we are doing some grouping on URL in order to eliminate duplicates at search time. I haven't made any tests on that, but subjectively it doesn't really make a difference in performance for us. So I turned it on and off and made some searches. It's answered as it used. We're doing some faceting. Some of it is the same as British Library is doing. That's for host and domain. One is quite insane, which is a URL faceting, because we have about these 6 billion unique URLs across our whole index. And we thought it would be an interesting challenge to facet on them. Well, the good thing is that we just had this, Kristen, you had this presentation with the nice layer where you had this list of URLs and the occurrences. Well, that's a facet on URL. Oh, sorry, what's that? What's that you?
Gina, I think. Yeah.
Gina, sorry, I missed you. So, yeah, it's about the same, yeah. So you just showed us a use case for it, instead of just being a tech demo. So thank you for that. Okay. All in all, I would say that with the URL faceting, we're doing a heavier job than British Library is currently doing with the setup. If we turned off URL, it would be a lot lighter because we don't have this links facets. We're actually planning on adding that, but due to technical reasons, we can't do that right now. Again, long story for later. Sorry?
Just the faceting, you do it on all URLs, but how about domains? Is that?
Domain and host and domain are separate facets from URL, yes. So,
okay.
So a URL facet, a host facet, a domain facet, what was it, crawl, facet, format facet, and domain.
Okay.
Yes. Good. Okay. What we have, our special brew is, well, it's Solr 4.8.1 for, again, long story. And we have a patch that we made ourselves, but it's really not necessary for this kind of setup to work. I'm sure it helps. I'll come to that later, but you can do it without. We're using all of the work from the UK Web Archive for the indexing as well as the schema they set up. And we put the technical feature called doc values on all the large fields where we're going to facet on. Those of you not familiar with Solr, let's just say that when you read about it, you will see that it is highly recommended to put it on. And for shards this size, it's absolutely essential because you can't facet technically without having doc values on such large fields. There's an internal limits in Solr that breaks down when there are more than, I think it's 2 billion references to values. Long story short. It's just a little warning. If you're building on this size, remember your doc values. So that was Solr version and schema, and we have Solr config left. So where we did absolutely nothing. Well, of course, I think you need to tweak a few things, but we really didn't do anything to optimize anything. We might get around to that at some point. But so this scaling thing. So we have this box. It could be a lot smaller. Now it's quite large. But we would like to see what happens if it changes parameters. This is what scaling is all about, predicting scale at least. So we tried having our test from before, which would be the very dark blue candlesticks, which you hopefully will remember from the previous slide, which is for all the 16 cores on the machines, which are hyper-threaded, which all Intel's processors are, at least for servers. So we tried adjusting the amount of CPU cores available for the Solrs. How important is CPU for this kind of search? And as you can hopefully see, I would say that about at least the 2 candlesticks to the right of each group, maybe the 3 and the 4th, are about the same. We could live with those. To the far left, we have only 2 cores running this 22 terabyte index, and if we do that, the performance times gets a bit icky, at least for the large result set. So don't do that. Don't use a dual core machine to host your net archive search. But for this, I would say we could get by with about 8 cores hyper-threaded. So for search, at least for our scenario, this machine is slightly overpowered in the CPU department. Which means there would be room for further scaling, by the way. But
quick question about that.
Yes.
So it looks like the 2 cores, the trend is exactly what you would expect. It looks linear.
Yes.
Without that
without that, yes.
Despair or whatever it was called. Why does that pit despair occur when you add cores? It seems counterintuitive.
I would say that running 2 cores with 25 shards of that size is so insanely unbalanced that what really happens in the near details, I wouldn't dare guess, because you're hitting some other things.
So it becomes disposable as a result.
Yes, it really, well, I could have run it with 1 core. I kind of regret I didn't do that just for fun, but nobody would go that far. There was a clear trend here. When you move below 8 cores, you can see that the response times goes high up. So.
Can you scale Solr across the cores, really.
When you issue a search, each search through each shard will in practice be single-threaded. So ideally for a single user of the system, you would have the same number of cores as you had shards, which would ensure that all CPUs are in work. But if you add more CPUs, it might help in a multi-request scenario with multiple concurrent requests, but it wouldn't help in a single search scenario. So this might also be what we're seeing here. If I reran this test with, let's say, 5 threads hammering the machine, we might get more out of our 16 cores. Again, this is very much from the basis of our usage, which is kind of single user, maybe 2 users at a time. So we have the same requirements as British Library. If your requirements would be to support 20 concurrent users, you would use that as your base test and hammering that way. And you might see a different pattern here. This is more an illustration of how we find out if we hit the right machine and if we can scale it further. So, tried another thing. If you're following the Solr recommendations after you're reading the mailing list, it will say that disk cache is absolutely essential for performance. At least a lot of people say that. That was Andy's funny slide with having enough RAM to cache the whole index. Well, we don't have that. Actually, when we're running at full capacity, we have 110 gigabytes free RAM. With this size of index, that's 1.49% of the full index size, which is 2 orders of magnitude away from the normal recommendation. So that's pretty special. So we tried having that. That's the one to the far left this time, which would be the blue one. So this is our standard setup. Then we tried eating some of the RAM by just running a small program that allocated the RAM and kept it live so that it wasn't flushed to swap space. Down to 98 gigabytes, 54, 27, and at the last 7 gigabytes. As you will see at the right side here, we're actually missing some of the measurements. We're missing the ones for 7 gigabytes and 27 gigabytes. That's really because it took so long that they just didn't get back within the time that the test was running. So what I can see from this is that as soon as we move past, I would say about the green line at least, which would be 54 gigabyte or about 0.25% of the index size, performance tanks. It really gets bad, and if you move further down, it gets absolutely unacceptable. We can't use it for search. So our solid state setup doesn't mean we don't need RAM for caching, but we can get by with this amount of RAM for our scenario. The important part about this is that we have multiple measurement points here. In this case, we have 6 points, 6 different configurations we tested with. I haven't done a logarithmic regression test on this, but I'm sure you could do it, and you could extrapolate a trend that said, well, what if we add double the amount of RAM? What could we expect our speed to be? Might be a fun experiment. We don't have the need. Our official requirement is to keep the median search times below 2 seconds for standard searches. So we're well within that margin for our setup, so no need for buying more hardware. But if you had the need, we would try that. Question for this? Yes?
What do we need if we were to have 10 concurrent users?
Yeah. That's a good question because I have a graph for that. Okay, good. Let's just try with 2 users to begin with, because it instantly goes bad. What we have on the left is, for this full, we have this 110 gigabyte of cache, and we're running a single user request at a time. As we can see, even within this little hill, which is our, can I show it with the mouse? Yes. I would consider from here to about here to be our standard searches, As soon as we begin to move into the 10 or hundreds of millions of hits or billions of hits, it's normally not something you hit with a standard query. It's more of a let's have all results from 2010 to 2015, which is not a requirement to serve within the 2 seconds. So just a technical detail. Anyway, this purple thing shows 2 concurrent requests hammering the server. As we can see, it moves our median up in the danger zone for the hill, but our worst cases are getting very bad. So it doesn't really work in that way, and I'm a bit sorry about that. Now, we are doing faceting on URL, so if we try turning that part off, cheating by changing the requirements, things change. So this is faceting without URL. It's still on host and domain of those 3 smaller faceting fields. We probably add a few fields in the same magnitude, so the end times will be a little worse than this, but still comparable. And what we can see, this is testing with 1, 2, 4, 8, 16, and 32 concurrent users. And it's actually quite nice. We can see that things are growing at an exponential rate, but they should be, because we're doubling the amount of concurrent users for each test. Maybe it's easier to look at the median response times, where we can see, well, the median response time for 2 concurrent users is actually not the double of 1 concurrent users. It's 85 compared to 70. The median response time for 4 concurrent users is not the double of 2 concurrent users. So it's actually relatively faster to have more users. That really just means that we don't utilize the machine 100% with a single user. So that's technical. It's just part of measurement. So, but when we move from 4 threads to 8 threads, suddenly the median doubles. And the same thing that we move from 8 to 16 and 16 to 32, it's a double each time. So that means that the sweet spot for this machine is somewhere around or between 4 and 8 concurrent users, which will be, it makes no sense to have more concurrent users, you could say. You don't gain any higher throughput with that. Running the numbers of this means really that for this setup with this reduced faceting features, we could support about 10 concurrent requests per second with this machine. Whereas with the big URL thing, we could only support half a request per second. So, something to ponder. Should we have that? Should we have it not? I don't know. But there are ways to cheat. Oh, brilliant! It was the right slide. I already cheated once by saying let's dial down our requirements for faceting because we know that's kind of heavy. Okay, is there other way to cheat? Well, what I plotted here is the blue ones are without faceting. That's just raw search time. Search for something, get 10 documents back. So it's to have a baseline in order to see how much can we gain from adding features or dialing on something. The orange ones, which only have 66 results returned and nothing in the heavy area, that's plain Solr faceting. We can see that it has a mean response time of 1.4 seconds, which is not bad. But sorry, the median response time, but the mean response time is 8.5 seconds. What this really means is that a lot of the searches are quite fast with Solr faceting, but our worst cases are just horrible. They hit those 20 seconds, 30 seconds, I don't know. I have the numbers for those interested. And again, I should have left this running more than 10 minutes because we have a few measurement points for the Solr test because it just took so long. So that leaves 2 of the other candlesticks. The green one is sparse faceting, which is kind of trying to do stuff smarter than Solr with regard to large-scale faceting. I urge you to take a look at the GitHub page. I made it. And I think it works very well for our setup. That actually delivers performance within our parameters, but only just. As we can see, those were the green candlesticks. some of the times actually gets around these 2 seconds, which were our design goal. But thinking back, faceting was a 2-stage process, distributed faceting. There was the first initial, we do faceting on each shard, and then there was a second fine counting, which means that we get the right numbers instead of just approximate numbers for each of the facets that we return. If we can live with imprecise numbers, we don't need the second round of requests for faceting. So that really means that it might state you have 10,000 hits on the domain foo.uk, but the real count might be 12,000 or something like that. If we can live with that, well, then we get the purple times, which are great. Not really more costly than, well, they are more costly, but comparatively to the correct counting of facets, they're dirt cheap. So it might be worth considering, maybe you could have 2 modes in a Solr setup. Are we going for precise results? Are we just approximate to see where the trend is going? And you will gain a lot of performance that way. This whole 2-phase thing is actually also the reason for this hill that the pit of pain that I hinted to earlier. Because what happens here is for these range of result sets here, chances are that all the 25 facets will actually return a different set of top domains in the facet, just because of random chance. So that means that for the fine counting, all the facets need to fine count all the top whatever content our facet had. That really means that the second phase is very heavy for a certain range of searches, which is this hill that we see. And that is the penalty of distributed faceting that we make go away by not having the fine counting. It's really the fine counting we see here in this hill. So I think I need to explain that further over a beer. Let's just say imprecise results can give a huge speed up. Okay.
There's a question.
Yes, sorry.
I just ask, do you think the results you get without doing the fine counting
Yes.
are in the same ratio of accuracy as when the fine counting is done? So would you given the data might come back as random, would you sort of assume that the accuracy of the counting, when it's improved, actually stays in the same ratio of one facet to the next?
I don't have a slide for that.
Oh.
It's actually something I hadn't tested. It's a very good question. And I think it would be very worthwhile to run exactly the same queries. Don't care about response times, just care about accuracy, and plot the difference between the hits and see maybe when we're hitting this pit of pain, the accuracy goes down the toilet. It could be. And maybe in other ranges it would be very precise. And it would be a very good thing to do before enabling that for the users.
Yeah.
That's a good project. Yes?
Isn't it a hill of pain?
I refer you to Andy Jackson.
I like alliteration.
Well,
That's all
sure.
it is.
The pit is where it speeds up again, so it loses pace going up again.
I think when
You just
I
need to flip the y-axis.
no, but seriously, I think that's what it was. And what I happened to be
Right,
using
okay.
it.
I was confused.
It was the other way around.
I was worried I was missing something.
The hill of hell.
The hill of hell.
Okay.
What hill is down? The horrible hill.
The hill of horrible heaven? No, this is
No.
not very
Only here in such a debate.
I'm sure we'll find a better name later.
I do have another question, actually. Sorry.
Yes.
In all seriousness, were you keeping a track of the search terms? This isn't analysis of performance, really. This is about your corpus that were resulting in the kind of wacky, long return times. Was there did you get any hint of what was causing these really long?
But it really is about the number of hits.
That it's making.
So that's this very strong correlation that says between 1,000 and 100,000 hits, this is where the hill is. Well, as your corpus grows, the hill moves.
Yeah.
But still within this single corpus, it's very strong correlation between having this number of hits and being in this range of response times.
Which, you know, I mean, that's logical and that kind of makes sense. I guess really this is more in terms of, and are your users likely to use them? So therefore, does it actually matter?
I can't say because
No, of
we
course not. We don't know.
okay, we have a few. Ulrich, how many are playing with that? You are.
Yeah.
So we have one user,
Okay.
and I know we have at least one more.
Yeah.
But maybe I should try. And the problem is we're testing a lot on the system,
Yeah.
so our test queries get intermixed with the real queries.
Yeah.
So it's kind of a mess right now.
Yeah.
We don't have any user queries logged.
Because there will be a population distribution for the number of times that you triggered a search that went that long. So there's also another scaling in
Yes.
the occurrence
Yes,
kind of range.
yes, there is, and we would have to have log queries to
Yeah.
probably say something about that. I would say that just playing around with the system, you know, entering your own name, searching for teddy bears or whatnot,
Yes.
actually places you in the pit of pain more often than not.
Right, because that's okay.
Yes, those very few hits are kind of rare. Those very huge hits, very, very rare. That's searching for and or to or be,
Yeah.
the Danish equivalents, of
Yeah.
course. So the pit of pain is very real
Yeah.
for this subjectively at least.
Yeah. So if you actually strip out the outliers, it becomes a bit of a bell curve, really.
Yes.
If you're occupying that kind of medium
Yes.
space in the bell curve.
So that also really means that we cannot just use the average of the mean across all our search tests, because that's what's stated here on top. If we look at the best case here, where we have no, let's just take the third one, the green one, that's sparse faceting. That's what we're using right now. Well, the median is below 200 milliseconds.
Yeah.
Hooray!
Yeah.
We're happy. Well, no, because our users will probably hit those two seconds more often than not. So that's what I mean. But please visualize your data, because boiling data down to one single number is, I don't think I've seen a case where that works. Do I have any more? Oh yes. Sorry. This was for the URL faceting, which I admit is kind of insane, except we have a use case now. So if we remove that, put it down to a more manageable level, which is lighter than what British Library is doing, but should be in the same ballpark when we add the features that you have. Then we can see that Solr faceting is actually, which is the orange thing still, it's actually still capable of delivering results within our requirements. So even in the hill, it only have response times about, I don't know, 1 second. So it's not because Solr faceting is bad, it's just because we're trying to use it on something a bit insane. On the other hand, the standard result sets, it doesn't really matter whether we are skipping the fine counting or not for this setup, because it's all so fast. It's down, yeah, you can see the mean time is around 100 milliseconds for searches in this, so it works fine for us. So, to wrap this up, thank you for listening. I'm sure something I've said was quite well confusing. The only thing I'll say about this is that the gut reaction to solid state drives is they're expensive and they break down. 1, they're not, and 2, they don't. Time is now. 5 years ago it was horrible. Nowadays it's very cheap, at least if you buy consumer drives. You might have problems getting a deal through with your organization. Hit them hard. Questions?
So Solr is a well-known search system in the commercial area too.
Yes.
Is there any size, because I have said the same amount of data in that area that you know of?
They're bigger. I was to Lucene Solar Revolution this year. Sorry, let me start. I was to Lucene Solar Revolution last year, and there the largest number that was mentioned was 80 billion records. Unfortunately, no index size corresponding, so I don't know really how large that was. But for this year's, there were more than one that said they had passed 100 billion, and index size in excess of these 22 terabytes. I think one had a 100 terabyte SolrCloud running on solid state. I didn't get the details of RAM setup and all that. So this is the scale we're talking about, which is capable of. Sorry, that was the same time. Let's try.
One question, what do you mean by SolrCloud?
SolrCloud is what we're using for search. It's really just treating all the shards as a single logical index.
So that means a lot of Solr processes running?
In our setup, we're running independent Solr processes. The normal recommended way is to have one Solr setup and have it host multiple shards. The reason we don't do that is it would require an enormous Java heap, which Java doesn't like. So that's more of a technical garbage collecting question for Java. Okay. Really, maybe we should run 4 Solr installations, each hosting 8 shards instead. That would be better. I don't know. We haven't fine-tuned that part yet. Yes?
Do you have a feeling for what, going back to the timing stuff, what the difference would be if you used spinning rather than SSD?
Let's just say that we did an intensive testing of that 6-7 years ago and never looked back.
Okay, so significant.
Significant, but it really depends because going back, I have too many slides here. Going back to this, well, you can see tape in one end and RAM in the other end, but you could reverse the less than signs and have price instead. So
that's your trade-off.
Yes, that's your trade-off. And question if we build this on spinning drives, how much RAM would we then need to compensate for the slower seek times? Yeah. And it would be an interesting experiment. Our general experience with this tells us that it's cheaper and easier for us, at least, with the setups and the requirements we have. Just forget it, just put solid drives in it and add RAM until it works. And really, they're so cheap nowadays, so why bother?
You think you can keep up doing that? Because how much do you harvest every year?
Well, as we have 500 terabytes now, we've been harvested for 10 years. I would say at least 50 terabytes per year. But I think 110 terabytes.
120 last year, and this year, oh no, was it 2014? Was it 110?
110 terabyte for a year.
Yeah, and we stopped. We didn't make this the last port call because of the budget.
Oh, okay. But the nice thing about this setup, we just put new shards in the machine until it's full. We have done that, and the machine is full. We're buying a new machine, 25 drives. Fill them up one at a time, one shard at a time. So we can scale horizontally. It would be a lie to say forever, because of course some other factors comes in, but we can scale a long way from here. And when we reach, I don't know, 10 times what we have now, 10 machines, we might have to reconsider our strategy. But we should be safe for some years. Point is that performance doesn't really go down by adding a new machine. It does a little bit because it's always the slowest shard that dictates the overall speed. So the chances of a search being a bit slower will be higher the more shards we add. But again, they're pretty fast to begin with, so we have some slack. Not saying you should build this. I'm really saying try and measure. Try and see where adding stuff will take you by having multiple measurement points. Do the visualization thing because it really helps seeing what is going on here. Yes?
Could you just get back one slide to the previous graph? So,
yes? One more?
I'm still a little bit obsessed with this hill of pain. If I'm reading this right, 5 to the 10, 10 to the 5 and 10 to the 6 seems to be a bit of a sweet spot, really, where all of the searches are around the same.
Sweet spot. Worst spot, yes.
There's very little delta between minima and the 29, the 9.
Yes, I'm about to say.
It feels like that there's something meaningful, that everything is kind of stabilizing around that. And again, without knowing what the frequency looks like, whether that represents the majority of your search results as well, do you think there's something meaningful? The fact that, apart from the orange one, which we agree that there's some, it's a bit extra. Does that tell you something about your faceting?
Okay, what is the time?
4:30.
4:30. Is that good or bad?
Good. We have half an hour.
Okay, so everybody close. Everybody. No, I can do it in 1 minute. So, point is, this is two-phase. First phase, we perform the search across all the shards, and they deliver a preliminary result. So that's fine. It takes more or less about the same amount of time as long as we are below, I don't know, 10 or 100 million hits. It doesn't care. So we have a facet. Let's just say it's domain names as a case. We get a list of the top X domain names from each shard. Okay. So when we need to find count this, let's just say we have domain names A and B from the first shard, and we have B and C from the second shard. So logically, we still need to ask about domain name C from the first shard and domain name A from the second shard, because we haven't had that information yet when we have merged. So the point is, at some amount of hits, depending on your corpus size, we will have the maximum amount of different domains in the result sets from each shard. Because the more diverse domain names they have in the top X result, the more extra requests we need to do in round 2 in order to get the proper counts. So this is really maximum entropy for the facets that you're having. And it's very clear, and it's extremely clear in Andy's measurements, also because he had insanely large facets. The 100 limit. And oh, by the way, yes, the more entries in a facet you request, the higher this hill will be. This is for 25 entries in each facet. And if I make it 100, the hill will be, I don't know, not twice as high, but markedly higher.
So actually, if you reduce your shard size, you might end up with a longer search time, counterintuitively, because you've got more merging to do on the fine count.
Yeah, that's actually a very good point. I think maybe the top of the hill would be higher in this case. Yeah. Yes.
Okay, interesting.
Well, no, because the aggregator section is the serial part of the process, right?
Yeah.
It's only the first. It's the searches which are parallelized, but the aggregation and then the second phase is like it's almost n squared. It's not quite. So yeah, it's kind of yeah.
We'll have to test that. But it is an interesting. It would be another great way of testing, trying the shard size.
Yeah.
Try how does it scale with different shard sizes. Good experiment. We don't need to this whole 25 shard thing for us. Just do it with 2 shards and 4 shards and measure on that. And then 8 shards, please, so we can have a trend.
Cool.
Do that and publish.
See what I can do. I need a 22 terabyte SSD box.
£7,500 current consumer prices.
Thank you very much.
Okay, admittedly, in order to run this, you need to have a controller capable of handling that, capable of delivering a fair amount of IIPS, whereas our peak was 90,000 IIPS. I really don't know if that's a lot or a little for a disk controller, to be fair. I don't know much about that part of hardware. And you need to have a system that can support 25 channels and all. So the price of building such a machine is quite a lot higher. My point is just, it's no longer the SSD drives that are hideously expensive.
But you're running all this directly in a host. There's no virtualization.
Bare metal. We are actually running bare metal for most of our search servers, but that's just because it has always worked for us. I'm pretty sure that for standard search, lower scale search, is really no problem running it virtualized. But for such a setup where we know this machine will never be used for anything else, don't have this extra level of interaction.
Okay.
That's also the same reason why we used local SSDs. We did some testing on a remote system which also had SSDs, and it turned out it was about 3 times slower to have a remote mounted SSD storage device, at least for our setup. Your mileage will vary, may vary, of course.
Then one more question: how are you backing up all this data?
Oh, that's exceedingly simple, as we have static shards. It's just a copy of each shard. So thank you for asking, because that's actually one of the selling points by using this static approach, as backup is trivial. Because with large indexes, there's kind of a backup problem, because how Well, technically, it's not a problem backing up a live index in Solr, but it's more of a hassle instead of just having static files and copying them. So, another problem solved by doing it the, well, simple way, I would call it. It's not a complicated solution.